Welcome to this in-depth explainer, where we are going to explore the fundamental physics powering modern electronics. You know, every single tap, swipe, and search you make on your device is actually governed by a strict set of microscopic rules dictating how incredibly tiny particles move. So today, we're unpacking exactly what those rules are and how engineers have harnessed them to build the modern world.
It's kind of a fascinating paradox when you really think about it. How exactly does the totally random, chaotic vibration of particles somehow create the absolute precise logic of modern computers? Well, to answer that, we are going on an epic journey of scale. We'll start way down at the invisible, chaotic level of single electrons, move up to the macroscopic devices you use every day, and finally push right up to the sub-10 nanometer quantum limits, where, honestly, everything we know starts to break down. Here's our roadmap for today's explainer. We'll hit random motion and Fick's law, the elegance of the Einstein relation, the survival dynamics of minority carriers, p-n junctions, the secret of BJT amplification, and finally the non-Fickian laws of the nano era.
Let's jump right into Section 1, Random Motion and Fick's Law.
Okay, so let's dive into this microscopic world where particles are in a state of constant, random Brownian motion, totally fueled by thermal energy. Basically, at any temperature above absolute zero, particles inside a semiconductor lattice are constantly vibrating, crashing into each other, and wildly changing direction. Now, there are two main ways to actually move a charge here: drift and diffusion, and the contrast between them is huge. Drift is basically a forced march. You apply an electric field, and particles are deterministically pushed in one specific direction. Diffusion, on the other hand, is driven entirely by heat. It's a probabilistic, spontaneous spread, where a massive group of particles does a random walk from an area of high concentration to an area of low concentration. And this brings us to Fick's first law, proposed by Adolf Fick way back in 1855. Fick actually borrowed the math from heat conduction to prove something pretty incredible. He showed that even though individual particles act with absolute chaos, when you zoom out, their collective behavior produces a remarkably smooth, predictable flow. They're simply trying to spread out and maximize the system's entropy, flowing perfectly down the concentration gradient. But here's the catch: when we apply this to semiconductors, we aren't just moving neutral molecules around, we're moving charged particles, specifically electrons and holes, which act as positive charges. Because electrons carry a negative charge, their physical movement down a gradient and the resulting electrical current flow in literally perfectly opposite directions. Can you believe that? It's this fundamental, counterintuitive quirk of physics that literally forces us to draw every single circuit diagram backwards today.
All right, moving on to Section 2, the elegance of the Einstein relation.
Let's fast forward to 1905 and see how Albert Einstein connected these two forces, drift and diffusion, in an incredibly elegant way. Honestly, this is one of the most beautiful insights in solid-state physics. The Einstein relation brilliantly illustrates that drift and diffusion are essentially two sides of the exact same physical coin. Einstein realized that whether a particle is being dragged by an electric field, which we measure as its mobility, or whether it's thermally wandering away, its diffusion coefficient, it is fighting the exact same microscopic obstacles in the crystal lattice. Because the underlying collisions are exactly the same, the math governing both movements is permanently linked. To put a number on it, at room temperature, which is roughly 300 Kelvin, this profound relationship hinges on the thermal voltage, which comes out to exactly 25.85 millivolts. This highly specific number serves as the ultimate scaling factor for all semiconductor transport models. It essentially represents the baseline thermal energy that's pushing these particles around before we even hook up a battery to the system.
Now for Section 3, survival dynamics of minority carriers. So the absolutely crucial point here is what happens when we inject excess carriers and disrupt that perfect thermal equilibrium we just talked about. In any semiconductor, you have majority carriers, which are everywhere, and minority carriers, which are rare. And here's the secret: the entire magic of modern electronics relies on manipulating these rare minority carriers. When we inject them into a region where they really don't belong, they start to diffuse, but their days are numbered. Eventually, they're going to bump into a majority carrier and recombine, essentially annihilating each other. Think of the minority carrier diffusion length as a strict measure of survival. It dictates exactly how far a lone particle can statistically wander in hostile territory before being completely eliminated.
Which leads us perfectly into Section 4, the p-n junction and the application of diffusion.
This whole concept beautifully sets up how we harness those survival dynamics to build a classic p-n junction diode. A diode is the absolute fundamental building block of electronics. It lets current flow in one direction, but perfectly blocks it in the other. When you apply a forward voltage, you lower the diode's internal barrier. Suddenly, minority carriers just flood across the junction. But because of that survival dynamic we just looked at, their numbers naturally dwindle the further they travel into the material. This creates this beautifully steep exponential decay profile. They are quite literally fighting to survive their journey, and their decaying numbers dictate the exact amount of electrical current we end up measuring.
This quote really hits the nail on the head. A diode is not just some simple on and off switch. Its entire real-world performance, like how fast it can switch states or how well it stops reverse current from leaking through, is dictated 100% by these underlying Fickian diffusion rules. The chaotic physics of these tiny, microscopic particles directly controls the macro performance of the device you're holding in your hand right now.
Okay, Section 5, the secret of BJT transistor amplification. Now we reach the real climax of engineering, actually using these rules to amplify signals with bipolar junction transistors, or BJTs. If diodes are the one-way streets of a circuit, transistors are the traffic lights that make complex logic and computing possible. Inside a BJT, we are basically running a microscopic, high-stakes survival game. Step 1, carriers are injected from the emitter. Step 2, they have to cross this treacherous, ultra-thin region called the base using absolutely nothing but random thermal diffusion. If they manage to survive that crossing without recombining, we get to step 3, where they are aggressively swept into the collector. This process is exactly how a tiny little input current at the base can control a massive output current at the collector.
To make a perfect transistor, engineers take all this complex physics and distill it down into two distinct goals. First up is the base transport factor. The goal here is simple: ensure the absolute maximum number of carriers survive that dangerous crossing without getting wiped out. Second is emitter injection efficiency. This is all about ensuring we don't waste precious energy pushing the wrong particles backwards.
And the results of modern engineering here are absolutely staggering. Thanks to nanotechnology shrinking that base thickness down so it's much, much smaller than the diffusion length, modern BJTs can achieve a base transport factor over 0.99. That means 99% of carriers are surviving the obstacle course. It's a truly incredible triumph of manipulating Fick's original laws. Now, to perfect that second metric, the emitter injection efficiency, engineers rely on a really clever trick. They heavily dope the emitter with impurities to physically restrict any wasted reverse diffusion. By making the emitter vastly more concentrated than the base, they effectively manipulate the Fickian math to force a massive asymmetric forward injection. They basically stack the deck so the diffusion has absolutely no choice but to flow exactly where we want it to.
And finally, Section 6, non-Fickian laws in the nano era.
So as we keep pushing Moore's law and shrink these devices down below 10 nanometers, something wild happens. Fick's assumptions from 1855 finally start to fall apart. The spaces inside the chip become so unimaginably tiny that carriers can actually cross the entire gap without hitting anything at all, a phenomenon we call ballistic transport. We also start seeing hot electrons that haven't even reached thermal equilibrium traveling at impossible anomalous speeds of 94 square centimeters per second. And under these extremely high densities, the particles start colliding with each other in complex, nonlinear ways, totally breaking the traditional models of diffusion we've relied on for decades.
To push beyond these classical limits, modern engineers can't just rely on simple pen and paper equations anymore. They're introducing incredibly complex heterojunctions made of wide-band gap materials to force entirely new quantum behaviors. And to actually understand what's happening, they're utilizing advanced quantum Monte Carlo simulations. They literally map the erratic, non-equilibrium behavior of individual particles in real time to design the next generation of futuristic chips. Yet, even with all these crazy nanoscale anomalies popping up, we definitely shouldn't dismiss the classics. Fick's drift diffusion framework remains the permanent theoretical monument in the history of solid-state physics. It is the foundational blueprint. It's exactly what allowed us to progress from simple thermal experiments in the 1800s all the way to the macro networks of billions of microscopic transistors sitting inside your phone right now. Which leaves us with a pretty profound final thought. Fick's laws gave us the entire computing revolution of the 20th and early 21st centuries. But as we cross this physical breakpoint where classic physics utterly fails, what mysterious new quantum rules will we need to master to power the computers of tomorrow? Thank you so much for joining me on this explainer. I really hope it sparked your curiosity, and I'll catch you on the next deep dive.